Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 40, Organic Chemistry 1. Today we will continue in chapter 9, Alkynes. Reactions of alkynes, hydration of alkynes, using mercuric ion-catalyzed hydration. Alkynes undergo acid-catalazed addition of water across the triple bond in the presence of mercuric ion as a catalyst. So acetylene with water in presence of mercuric sulfate and sulfuric acid, addition of HOH across the triple bond where the hydrogen will be connected to the carbon carrying more hydrogen, so it's Markovnikov orientation, and the OH will link to the carbon carrying more substituent to give vinyl alcohol, we call it enol, which tautomerize to the more stable keto structure. Mechanism: the alkyne will attack on the mercuric ion first, add to form vinyl carbocation, nucleophilic attack by molecule of water, oxonium ion, followed by deprotonation to form vinyl alcohol, organomercurial alcohol. Then the double bond proton transfer to form the carbocation, which is stabilized by a resonance structure, followed by ejection of mercuric ion again to form the enol, which tautomerize to the keto structure. This tautomerism is acid-catalazed, so the enol in the presence of H plus will add to form carbocation, which is stabilized again by resonance. The lone pair of oxygen will get down here between the carbon and the oxygen to form a double bond, and the positive charge will be on the oxygen. Proton transfer using a molecule of water to give the keto structure. Hydroboration-Oxidation of Alkyne. The reaction proceeds via anti-Markovnikov addition, thereby installing a hydroxyl group at the less substituted position. Hindered dialkyl borane like dicyl-amyl borane and 9-borobicyclic 3,3,1-nonane must be used to prevent addition of two molecules of borane across the triple bond. So R is a bulky group. This R could be this disecondary isoamyl groups, or the bicyclo system 9-boro bicyclo 3,3,1 non-borane. So using the bulky borane, we'll add one molecule, so H and Br2, to give vinyl borane, which upon oxidation with hydrogen peroxide in base will give the vinyl alcohol enol, which catalyzed under basic condition to the aldehyde. The mechanism of base-catalazed, the enol dishydrogen acidic in the presence of base will form the enolate ion, which is stabilized via resonance with the carbanion, so negative charge on carbon, which then attack proton transfer from molecule of water to form the aldehyde. If you would like to see a complete example, such but1N with Ca2BH to give vinyl borane. Upon oxidation of this vinyl borane with hydrogen peroxide base will give the enol, which tautomerize to the butyraldehyde. As you see, it starts with 4 carbon. You end up with 4 carbon. Here, terminal alkyne, and here is terminal carbonyl, which we call it aldehyde. Starting with terminal alkyne, hydrate with sulfuric acid water mercuric sulfate as a catalyst. You get the hydrogen attached to the carbon carrying more hydrogen, will be the terminal one, and the OH to the more substituted to give, after tautomerism, methyl ketone. If you do the hydroboration followed by oxidation method, then you get the OH on the terminal carbon and the hydrogen to the more substituted, and after tautomerism you end up with the aldehyde. No change in number of carbons from the starting material and the product, but one of them will be methyl ketone and the other one will be the aldehyde. One will be Markovnikov addition, which is acid-catalazed mercuric sulfate, and the other one will be anti-Markovnikov addition, which is the hydroboration followed by oxidation method. Identify the reagent you would use to carry out the following transformation. Here you have terminal alkyne, and it seems like the OH is connected here to the more substituted. Okay, so this is Markovnikov addition. How do you make Markovnikov addition? Via acid-catalazed hydration using water, sulfuric acid, mercuric sulfate. Here is a more substituted, yes. So how you do it? You do it with mercuric sulfate, catalyzed acid, water mixture. Oxidation of alkynes. Permanganate oxidation. First condition, cold aqueous potassium permanganate under neutral condition. If you use that, then you add OHs on the carbon-carbon bond. So it will be OH, 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 followed by dehydration, elimination of 2 molecules of water to form 1,2-diketo compound. If you have terminal alkyne, then you add again OH, 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 OH. After elimination of water, you will find that you get keto and you get aldehyde. again 1,2-dicarbonyl product. The aldehyde is sensitive to oxidation, so it will oxidize to carboxylic acid, and the final product will be alpha keto carboxylic acid, alpha keto or alpha carbonyl carboxylic acid. When we have warm, basic, concentrated potassium permanganate, the diketone will undergo what we call it oxidative cleavage. So after the formation of C double bond O on here and C double bond on this carbon, then this will break completely to form carboxylic acid, but under the presence of potassium hydroxide, this will be potassium salts. So we need to acidify or neutralize the medium to obtain carboxylic acid as a final product. If we have this compound terminal alkyne give carboxylic ion and formate ion. Under these oxidizing conditions, formate might oxidize further to carbonate, which then became CO2 and water. So we have alkyne terminal, we oxidize under this condition, we cleave this to carboxylate potassium salt, and this one will be formate, which has which goes further oxidation to carbonate, and the carbonate will be CO2 and water after the neutralization, and this carboxylate will be carboxylic acid. If we have one butane, 1, 2, 3, 4, so but1N under the condition potassium permanganate, potassium hydroxide, water and heat, followed by acidification, then will be 1, 2, 3 carbon containing that carboxylic acid, propanoic acid, 1, 2, 3 propanoic acid, and this part will be CO2. Ozonolysis. Ozonolysis of an alkyne followed by hydrolysis cleave the triple bond and gives 2 carboxylic acids. So if we started with disubstituted acetylene, first step ozonolysis, second step addition of water, we get this carbon will be COOH and this carbon will be COH. So 2 different carboxylic acid R and R prime. Here we have 2 carbon will be acetic acid. Here we have 1, 2, 3 carbon, this will be propanoic acid. Here we have 1 carbon and here we have 1, 2, 3, so this will be propanoic acid, and for this one will be formic acid. Reacting alkyne with ozone will lead to the formation of ozone adduct as a first step. Ozone adduct is not stable, will undergo ring opening to give either ionic species or biradical species which are in resonance with each other. followed by ring closure to bicyclic ozonide. This bicyclic ozonide either lose oxygen to form dicarbonyl, or ring opening followed to form anhydride, followed by hydrolysis of water if we add water, and that will give the carboxylic acids. The mechanism is more complicated than that. If you would like to read more, go to Journal American Chemical Society, 2001, volume 123, page 6127. Just to simplify, this is the biradical as an example of the ring opening product of the first step. Homolytic fission in here will give biradical. Rotation around this single bond will give the radical in here. Oxygen and the carbon get together to form a three-member ring. And this carbon radical with this oxygen radical will form a bond to form four-member ring. Now, if this one ring opening this way, that will give the anhydride. The anhydride, upon hydrolysis with water, oxygen will take H and this carbon will take the OH and give the carboxylic acid. If we have a reducing agent like triphenylphosphine, will take the oxygen out, okay, and leave this double bond formation in here and double bond formation in here to form the 1,2 dicarbonyl compounds. So if we have the alkyne with ozone in dichloromethane acetone mixture, and then followed by addition of triphenylphosphine at very low temperature, the product will be the 1,2 dicarbonyl compounds, and triphenylphosphine is used to just quench the ozonide intermediate. You may read more on that if you would like on Organic Letters 2020, volume 22, page 7424. An unknown alkyne undergoes oxidative cleavage to give adipic acid and two equivalent acetic acid. Propose the structure of the alkyne. We know that the alkyne, upon ozonolysis followed by water, gives carboxylic acids. Well, we have adipic acid, so in here COH and here COH, and two equivalent of acetic acid. So the triple bond cleaved to give carboxylic acid on the right and carboxylic acid on the left. So what we are going to do to solve this is put the carboxylic acids in front of each other. So one is carboxylic acid here, and I put here one acetic acid. On the other side, carboxylic acid and the carboxylic acid. Well, second step is taking the oxygen out. We have now triple bond, 1, 2, 3 bonds, and here 3 bonds, 1, 2, 3. All what I have to do is fuse them together in one triple bond, the same to this. Okay, so what I'm going to do is to fuse these together to form a triple bond, and fuse these together to form one triple bond. Here we are, so the compound is DK28-diene. This is a compound. Okay, so if I cleave this, make this carboxylic acid, this is carboxylic acid, cleave that, this is carboxylic acid, this is carboxylic acid, we get these products. Azide-alkyne Huisgen cycloaddition. It is a reaction between alkyne and azide to give 1,2,3 triazole compounds. So the 1,3 dipolar, 1, 2, 3, positive and negative, so dipole, or we can say it is 3 plus 2 cycloaddition reaction. Either the nitrogen will be facing the nitrogen containing carrying negative charge will be facing the right hand or the left hand position to give either 1,4 disubstituted or 1,5. So under Huisgen condition, both products are obtained. You can read, if you want to, more on that, Journal American Chemical Society 2005, volume 127, page 210. More advanced study of this reaction reported that using copper 1 as a catalyst, the reaction goes radioselective to afford or 1,4 disubstituted, 1H123 triazole. Other studies showed that using ruthenium as a catalyst in dioxane as a medium provide 1,5 disubstituted 1H123 triazole. You read more, Journal American Chemical Society 2008, volume 130, page 8923. Reaction of carbenes and carbenoids with alkynes. The Diazo method is based on carbene decomposition reaction of alkyl diazoacetate that takes place on exposure to radiation, heating, or catalyst. Addition of the resulting free or complex carbene to a triple bond gives cyclopropene 3 carboxylate ester. So we start with alkyl diazoacetate under the influence of light, heat, or catalyst, decomposition losing N2 to form carbene intermediate, reacted with alkyne to give the cyclopropene product. By using rhodium compounds like rhodium acetate as catalyst for this process, it is possible to obtain cyclopropene 3 carboxylate ester in high yield, even at room temperature, from both terminal and internal acetylene. On the other hand, using 5% copper iodide as a catalyst in acetonitrile led to insertion between reaction into the alkynyl hydrogen bond to produce 3 alkynoids. So we have terminal alkyne with alkyl diazoacetate Catalyst copper iodide in acetonitrile at room temperature provide 3 alkanoids. 1, 2, 3. If you'd like to read more on that, go to Organic Letters 2011, volume 13, page 2388. Let us examine our skill in organic synthesis. Develop synthesis for the following compounds using acetylene and compounds containing no more than 4 carbon atoms as your organic starting materials. Cis 1-ethyl 2-methyl cyclopropane. Here we have the structure. Retrosynthetically, this compound with ethyl group, methyl group, and cyclopropane ring can be obtained from methyl, ethyl, and alkene. So we can get this compound from the alkene reaction with carbene. The triple bond reduction can lead to the formation of this alkene. So starting from this compound, we can get that one. How we can get this compound from alkyne? We can get this from the acetylene compound by adding 1 ethyl bromide and 1 methyl bromide to acetylide of this. So if we have acetylide with ethyl bromide, we can get this compound, and methyl acetylene we can get from again acetylide with methyl bromide, and we can get the acetylide from acetylene. So this is the retrosynthetic pathway to the desired compound. So starting with acetylene with sodium amide and liquid ammonia forms acetylide. React that with methyl bromide will lead to the methyl acetylide. Reacting this with sodium amide and liquid ammonia followed by ethyl bromide will lead to the formation of this alkyne. Reduction with poisoned catalyst like Lindlar catalyst will lead to the formation of the cis alkene. Reacting this alkene with methylene iodide, zinc copper as a catalyst will lead to the formation of the target molecule. Straightforward synthesis. How can you start with acetylene to prepare mesohexane 3,4-diol? So it's meso, so it's R and S configuration. If you draw it this way at the beginning and then you rotate that, carbon single bond, you can get the structure, the 2OH on the same direction, and the two ethyl groups are on the same direction. Here the OH and OH anti to one another, ethyl and the ethyl in opposite direction. So we can get this molecule either from the cis or the trans hex 3-ene, and we can obtain these compounds from their corresponding or from the alkyne analogues, okay, which will be no cis, no trans. This is linear molecule, so they are the same. But once we do the reduction syn addition, and in another pathway we can do that via anti addition, and we can get this by again syn hydroxylation, and here via anti hydroxylation. Let's see how we can do it. Of course, starting from here to this compound is straightforward. We mentioned before, first treat this with sodium amide liquid ammonia to get the acetylide, react this with bromoethane to get the butyne, treat that with sodium amide liquid ammonia, then another molecule with ethyl bromide or bromoethane, we get hex 3-ene. If we treat this compound with Lindner catalyst, we get the cis. To get the dihydroxylation on the same direction, we use cold dilute potassium permanganate. Here we are, we have the meso compound. If we start with hex 3-ene with sodium and liquid ammonia, we get the anti-hydrogenation, and we obtain E hex 3-ene. To get the hydroxylation, dihydroxylation anti, we first treat this compound with metachloroperoxybenzoic acid, to form the epoxide. Then the epoxide is treated with dilute water, acidified water, to give ring opening and finally the anti-addition of 2OH will lead to the formation of the mesohexane 3,4-diol, 3R4S. I hope these two examples provide enough information of the strategic way to solve synthetic problem. Here is an example of being smart. How you can start with terminal alkyne and transfer it to again terminal alkyne with 2 extra carbons. Starting with the alkyne, treated with sodium amide liquid ammonia, and then add the two carbon you need, ethyl bromide. It will be CH2CH3. Now treating this with reagent like potassium aminopropylamide, which has two sides. One acts as a base and one acts as an acid, abstracting proton, formation of double bond, abstracting hydrogen and form alene. Again, this side acts as a base, double bond will be triple bond, and the double bond will be a single bond. So you have this compound now. Once again, taking the hydrogen, forming a double bond, abstracting the hydrogen, forming alene, one more time, triple bond, abstracting hydrogen. Here we have the alkyne, but under this condition, another molecule will have this hydrogen. This is a very strong base, it's acidic. So we get the acetylide, and to stop the reaction, we have to add acidified water to get the desired compound. They call this Alkyne Zipper reaction. Okay, and I found it's very smarty model of how the chemists think about selecting reagent in organic synthesis. See you in the coming lecture.